Hi everyone, welcome back to the channel and welcome back to another video on probability intuition and probability theory. This video is supposed to be a continuation of the last video I uploaded on probability theory. I'm going to upload a link. I'll leave a link to that video in this video and in the description box below, linking to that previous video. So if you need to watch that before watching this, it's available. Now let's have a brief recap of what we discussed in the last video. So in the last video, we looked at the frequentist approach to calculating probabilities, and then we looked at the Bayesian approach to calculating probabilities, and we concluded that the frequentist approach makes use of empirical data, past experiences, to extrapolate and determine probabilities of future uncertainties. And the Bayesian approach, on the other hand, just makes use of personal feelings, gut feelings, personal opinions, I guess. I guess the Bayesian approach is something you would see a psychic do. A psychic wouldn't use data. A psychic will probably use the Bayesian approach. Or a detective who's investigating a suspect or questioning a suspect they have never seen before. They don't have any hard data, or probably a first-time suspect. Probably have no records of any previous crimes. No clues, an investigation could use. So whatever information you're getting out of that suspect at that particular time would only serve so much. Ultimately, you'd still have to go with your personal hunch or your personal feelings in determining if that suspect is guilty of the crime or not. So at least off the top of my head, those are two people I can think of who wouldn't require a frequentist approach in determining the probability at that particular time. Now, for each of the probability types we introduced in the last video, they all have their corresponding mathematical formula. And in this video, I'll try to reconcile the frequentist approach with the mathematical formulas to show that they are the same. I mean, data practitioners for the most part use data, so I don't think we'll be using the Bayesian approach much in this video. I just brought it up, for the recap. But for the most part, our approaches moving forward will be frequentist, and all the mathematical formula we will be introducing will be surrounded around the frequentist approach. And I didn't introduce the math in the previous video because I didn't feel the need to introduce any complication. I just wanted something with easy logic and intuition that anyone watching the video could easily understand. Now let's continue with the recap. We identified three kinds of probabilities. We identified the joint, the marginal, and the conditional. So the joint probability, like we said, calculates the probability of simultaneous events. So if you have two random variables, one random variable x and another random variable b, the joint probability, another random variable y, the joint probability calculates the probability of simultaneous events in both random variable. So you could name your events across both variables, event A and event B, and use the joint probability to calculate the probability of both events happening at the same time. Remember, we used the keyword there for us was and. So the probability of event A and the probability of event B. The marginal probability, on the other hand, is really just the probability of just an event in a random variable, because it doesn't care about what happens in the other variable. The only thing we're interested in is the probability of an event in just one, random variable, regardless of the events in another variable. And then we also discussed the conditional probability, which is the probability of an event in one variable given an event that has occurred in another variable. So the keyword there was given. And remember, we said the given alters the space of all possible outcomes. So we take a snapshot of the original variable and we take instances of the original variable that will make up the snapshot. So this snapshot is just instances of the original data set. Not original variable. Instances of the original data set that fulfill our given requirements. The requirements after the given condition. And that's exactly what the conditional probability is. Now, note that we can apply these principles to multivariate data as well. So your data set doesn't just have to have two variables for these conditions to hold. We can use the same conditions for multivariate data, 100, 1000, 10,000, 100,000 variables. The principles work just fine. All right, let's get on with today's video. So imagine we're at a casino and you're about to play your favorite card game, poker, craps. I don't know what the card games are, but anyways, imagine you're at a casino, you're about to play your card game, you're about to roll a dice. Let's walk through some concepts. Now, imagine we have a fair die, because I know we could also have loaded dice. That's also a very, very common concept in gambling. I don't think I've ever seen a loaded dice or loaded die before. I don't think I've ever seen loaded dice or a loaded die before, but I know it's a very, very common concept. People talk about it a lot. But imagine for this example, we have a fair die. Now, a single roll of that die, a single roll of the fair die we have is only going to give us a 1 in 6 chance of any number coming up between 1 and 6. Just a 1 in 6 chance. And that number translates to 16.66%. And all the numbers on the die have an equal chance of turning up, because they just have one instance. We only have one instance of 1, one instance of 2, one instance of 3, one instance of 4, and one instance of 5 and 6 each. So we can say the die has uniform probabilities across all its outcomes and all its values. Now let's keep going. Imagine we have a second die that's also fair. It's a fair die. And if we roll the second die, we still get the same probability of each value on the second die, and the probability is still uniform. But here's something you need to take note of while we're talking about the second die. The outcomes from the first die we had do not affect the outcomes from this die, and the outcomes from this die do not affect the outcomes from the first die. And that's because of a principle called independent events. Both events from both die rolls are independent. They don't affect each other. So getting a certain value in the first die does not alter the value you're going to get in the second die. Take note of that. It's called the principle of independent events. Now let's take it another step further. Think about this question. What will be the probability of rolling an even number? Try and remember the logic from the last video and use that logic and intuition that we expounded on in the last video to answer this question. If you rolled a die, a fair die, not a loaded die, a fair die, what's the probability you're going to get an even number? Think about it. Now remember, in the last video I said we need two numbers. We need the number of desired outcomes and we need the number of possible outcomes. So let's think about these two numbers. What do you think the number of desired outcomes when you roll an even number, when you try to get an even number when you roll a die? What do you think the number of desired outcomes you're going to get is? And what do you think the number of possible outcomes you're going to get is? You're going to get 3 even numbers, because every die has 3 even numbers. You have 2, you have 4, you have 6. That's simple. And the possible outcomes are the 6 different values you could get: 1, 2, 3, 4, 5, and 6. So the probability of getting an even number with one roll of a fair die will be 3 over 6, which is half, which translates ultimately to 50%. So you have a 50% chance of getting an even number when you roll a fair die. Now let's make the question even more interesting. Let's make the situation even more interesting. What will be the probability of getting 2 even numbers? How do you think we'll go about that? This is where I'm going to introduce the mathematical formula. I know we can solve this with the logic, and we can solve this with the logic I introduced in the last video, but I'm going to do that at the end of this video with the Python notebook, and I'm going to leave the link for the Python notebook in the description. But for now, let me introduce the mathematical formula. So the mathematical representation for joint probability of 2 events is the probability of event A as a standalone event and the probability of event B as a standalone event. And as we concluded in the previous video, the probability of getting an even number when you roll one fair die is 50%. So the joint probability of getting 2 even numbers when you roll 2 dice simultaneously at the same time will be the multiplication of both probabilities, which will be 25%. That's just the mathematical representation. I will try to reconcile this formula with the dataset approach and the logic, the logic we created in the last video when we go towards the notebook. So stick around for that. So the table on your screen is a joint probability table, and it's typically used to document joint probabilities from 2 events in at least a 2-dimensional. It's a 2-dimensional table, so we're looking at the joint probability of 2 simultaneous events in a particular domain, and our domain in this instance will be the roll of 2 fair dice. And as you can tell, the numbers are similar because the individual probabilities are all similar, because like I said, the roll of a die has a uniform distribution, so you can expect that they are joint probabilities, would also have a uniform distribution. So for example, if we wanted to find out the joint probability of getting a 1 in dice 1 and say a 6 in dice 1, you just have to go to row 1, column 6, and that will give you the joint probability, which is 2.7%. But keep that idea in your head, because we're going to come back and refer to this table as we move through the slides. So let's look at some joint probability with frequencies logic and go back and refer to those slides. So if we wanted to know the probability of getting a 1 with dice 1 and getting a 1 with dice 2, how would we do that? Now, like I always say, like I've said, you need two things. You need, number one, the number of possible outcomes. In this instance, that will be 36. Now, let me make sense of why that is 36. Back to the table. So for every value we get for dice 1, let's pretend dice 1 is represented by the values on the rows. So 1, 2, 3, 4, 5, 6 on the rows. And the values we can get, the values we can get for dice 2 are represented by the values on the columns 1, 2, 3, 4, 5, 6. Now, for every number we get in dice 1 on the row, let's say we roll the dice, we'll roll a die, and we get, I keep mistaking the plural for the singular. Let's say we roll a fair die and get value 1. There are 6 different combinations we could pair that 1 with from dice 2. So we could have a 1 on dice 1 and have a 1 on dice 2. We could have a 2 on dice 2. We could have a 3 on dice 2. We could have a 4 on dice 2. We could have a 5 on dice 2. And we could have a 6 on dice 2. Now, if you apply that logic to the 5 other numbers for dice 1 and those combinations, ultimately we're going to end up with 36 different outcomes, which is why we have 36 cells here with the same joint probability. Again, dice rolls have uniform probability, so that kind of explains why all the possible combinations we could get when we roll two fair dice. I keep mixing those two up. When we roll two fair dice, gives us 2.7%. All right. So if we come back to the frequencies logic, we're going to get 36 possible outcomes. Now, what's the desired outcome? Like we said, we're looking for 1 from dice 1 and 1 from dice 2. What's the frequency of that outcome? It's just 1. Because dice 1 only has one instance of 1 and dice 2 only has one instance of 1. And the joint probability is 0.027. Because the probability that dice 1 will give you a 1 is 1 over 6, and the probability that dice 2 will give you a 1 is 1 over 6. So the joint probability will then be the number of desired outcomes divided by the number of possible outcomes, which is 1 over 36, which gives you 0.027 or 2.7%. As you can see, the table supports that assertion. Now, if we use the mathematical formula we brought up earlier, and you multiply 1 over 6 by 1 over 6, you're going to get 0.0027. Let's try another example. What's the probability of getting a 1 on dice 1 and an odd number on dice 2? Let's try to figure it out with the frequencies logic we learned in the last video. So the possible outcomes, again, this time is 36. Our desired outcomes this time is 3. And how so? So let's go back to the table and figure out how we would have, and figure out why we would have 3 possible outcomes, 3 desired outcomes for 1 in dice 1 and an odd number for dice 3. So for every time we have 1 in dice 1, how many odd numbers can we get from dice 2? There are just 3 odd numbers we can get from dice 2. That's 1, 3, and 5. So we can have 1 and 1 for dice 2. We can have 1 and 3 for dice 2. And we can have 1 and 5 for dice 2. So that gives us 3 desired outcomes. Let's go back to the definition. So the probability will then be those 3 desired outcomes divided by the total number of possible outcomes, which is 36, which comes down to 8.3. Refer back to the formula. I think I need to go back to that formula. Probability of event A multiplied by probability of event B. Now we can use the joint probability table to also get this result. All we have to do is add up the 3 joint probabilities for the odd number outcomes. So the probability of rolling a 1 and a 1 will be 0.027. Now, since the other probabilities are the same, we just have to multiply 0.027 by 3, which is 0.027 plus 0.027 plus 0.027. And what would that give us? That gives us 8.3%. Do you now see how helpful the joint probability table can be when you apply it for joint probability problems? It just helps you map out the combinations and make sense of where things should fit. So let's take a final example, and this time we'll be looking at conditional probability. So what will be the probability of getting a 2 with dice 1 given we have a 6 with dice 2? Our possible outcomes is still 36. That part's simple, but the part that's tricky now is the desired outcomes, which is 6. Because dice 1 and dice 2 are both independent events. So we have 6 desired outcomes. Let's go back to the table for reference. So for 2 in dice 1, we have 6 possible outcomes we can get in dice 2. So a number of desired outcomes will then be 6. So the probability then will be 6 divided by 36, which will give us 16%. All right, welcome to the coding section this is the coding section of the video. What you have on your screen right now is a synthetic data set that outlines all the possible combination of dice rolls. So on the first column we have dice 1, and on the second column we have dice 2, and for each value in dice 1 we have for the second column we have all the possible combinations that can go with that value. So for instance, for dice 1, where we have value 1, that value can be paired with value 1 in dice 2, it can be paired with value 2 in dice 2, it can be paired with value 3, all the way to value 6. And then for value 2 in dice 1, the same logic applies. And as you can see here, we have 36 outcomes. So this is the first reconciliation with the concepts we discussed during the slides, where we discussed all the possible outcomes from the roll of 2 die. And as you can see, we get 36 combinations. So that pretty much sums up the description of this data set. It's a very, very weird and different approach because no one uses a data set per se to solve dice problems, but it's just something I thought to use to just explain the logic and intuition behind joint probability, and I thought it would be helpful. So let's go into the notebook and explain what's going on. So as usual, we import pandas, the standard library for data sets and data frame manipulation. And then we load the data set with pandas and save the data set in a variable I have called dice_df. And then we pull out the first 5 rows of the dice data frame that we saw earlier right here. It's just the first 5 rows. All right, so let's get into some computations with should I bring that up? I should just leave it like this. Let's get into some computations we ran earlier during the slide. So the first computation, what's the probability of rolling a 1 with dice 1 and another one with dice 2? So like we always do every time, we find the desired outcomes and we find the possible outcomes. So the desired outcomes here will be all the instances in this quote unquote synthetic data set where dice 1 is equals to 1 and dice 2 is equals to 1. Let's try that manually. Where do we have dice 1 equals to 1 and dice 2 equals to 1? It will be here. That's the first outcome. And that's the only outcome. It just happens once. So the number of desired outcomes will be 1. And then our possible outcomes, like we agreed, will be 36. So the probability in this instance will be the desired outcomes divided by the possible outcomes. And as you can see, that gives us the 2.7% figure we saw in the joint probability table. I promise you there'll be reconciliation, and as you can see, there is reconciliation of values here. So this method works just as fine as the mathematical approach and method we learned during the slides. Now let's go on to the next code cell, and it wants us to find out the probability of rolling an even number for each dice. So again, we need to find out the desired outcomes. And what I did here was grab all the instances of dice 1 where the value is an even number. And as you can see, I'm using the modulo operation here. The modulo operation is the quote unquote remainder operation in Python. So essentially what this is saying is for every value in dice 1, if you divide that value by 2 and it doesn't leave a remainder, if the remainder is 0, and then we run the same operation in dice 2. So we go through all the combinations. If both values in the combinations leave a remainder of 0 when we divide by 2, then it fits the criteria. It's an even number on both, on both dice. So those are our desired outcomes. We could do that manually, but I don't know how long that will take. Let's see. It won't be this, it won't be this, it won't be this. So I know it won't be any one in value 1 for dice 1. So it will mostly be value 2, value 4, and value 6. So for value 2, where we're going to have even number outcomes for both dice, it will be 2 2, it will be 2 4, and it's going to be 2 6. So those are the 3 outcomes. So you can expect that for the other even numbers in dice 1, that's for 4, the values of 4 and the values of 6, we're going to have the same outcomes. We're going to have 3 outcomes each. So in total, that gives us about 9 outcomes out of 36 possible outcomes, which eventually comes up to 0.25, 25%, which is the same value we got when we ran the mathematical computation in the slide. So let's move on to another question. So this question wants us to find the probability of rolling a 1 with dice 1 and an odd number with dice 2. So let's get the desired outcomes. We need all the instances in our synthetic data set over here where dice 1 is equals to 1 and dice 2 does not leave, and dice 2 does not leave a remainder of 0 when we divide the value of dice 2 by 2. So essentially, the combinations of 1 in dice 1 and all the odd numbers in dice 2. And then the possible outcomes would happen to be the entire data frame, which is 36. So ultimately, the probability will be 8.3%, just like we calculated in the slides. Now, the final question here wants us to find out the probability of rolling a 2 with dice 1, regardless of the outcome of dice 2. So ultimately, it just wants us to calculate the probability of rolling a 2 with dice 1, which is the marginal probability, and it's just the probability of event A. So again, per usual, we grab the desired outcome, which is the number of all the sum of all the instances, or the number of instances where dice 1 is equals to 2, and we divide it by the possible outcomes, which is 36, and that gives us 16%. Link to the previous video, like I said, is in the description box. The code for this video will be provided in the GitHub link in the description box, and the dataset, the synthetic, quote-unquote synthetic dataset we created for this video, will be provided in the GitHub link in the description box. You can get everything you need there. So thanks for watching this video, and see you next time.